And good morning, everyone, and welcome to our second week of our sessions on vendor-neutral networking. So want to welcome everyone. Good morning, good afternoon, good evening, wherever you happen to be located across the globe. So this week, let me go ahead and bring in our schedule again. So we're doing standards bodies and the OSI model this week. So why are standards important to networking? What different standards groups are there out there, and what do they each have control over? For the upcoming schedule, we'll take a look at that kind of as we finish out today's session and look at what events we have coming over the next several weeks. So why don't we go ahead and instead look at what we're actually going to be covering today. So let me bring that in real quick. So this is going to be standards bodies and the OSI model as today's topic. So we'll go ahead and start out with the kind of general concept of standards. So we use communication protocols or standards when we communicate in modern networks and in modern network infrastructures. So these can be a lot of things you're familiar with. If you're going to a website, you're using the HTTP standard in order to do that. That is what allows us to have different types of browsers. So you might be using Edge, you might be using Chrome, you might be using Firefox, you could be using Safari, you could be using a number of different types of browsers, but because we have standards around things like HTML, which is how is a web page created, or things like HTTP, which is how a web server is actually going to receive requests and respond back to those requests, you have the freedom and flexibility to use different types of browsers to allow that communication to take place. And standards are nothing new. This is not something that is unique to networking. We've had standards for thousands of years, and literally thousands of years. So if we look at standards around weights and measures, many of these standards go back as far as about 6,000 years in human history. If you look back at ancient Egypt, ancient Mesopotamia, you had standards like the cubit. So the cubit was the length of, if I move that over so you can see there, kind of the inside of my arm up to the top of my middle finger was 1 cubit. Now, of course, I'm about 6.5 feet tall, so that length may differ on me versus some of the other people that are attending the session here today. So you had to create additional standards around kind of a rod. So you had a standard rod that represented the length of a cubit. If you didn't have that, and let's say you were doing a massive building project and you were receiving stones from several different quarries located around that geographical region, you wouldn't be able to use those stones if they did not fit to standards, if they weren't actually all the same length, the same width. So standards have been around for a very long time. If you look at the ancient Roman Empire, they had standards as far as the width of chariot wheels, because you had to ensure that that was the same width so that chariots that were going over a road, it would always create ruts in those same locations. So standards bodies is nothing that's new. And kind of a quick example. So normally I wear like my Ruckus wireless shirt when I'm delivering these sessions. This week I wore a different shirt for a very specific reason, and we'll take a look at it here. So this shirt is actually based around a standard. So it's got a series of binary numbers and says, if you can read that, you are too. So let's look at kind of that standard as an example, because it actually fits some of the things we're talking about today. And that standard is actually ASCII. So if I look at what we're seeing here on this particular slide, and let me go ahead and zoom in a little bit on our view. So if we look at these values, I can write an email, I can send that to you, and you can read that email. And it doesn't matter what platform you're on. It doesn't matter if you're on an iPhone device running iOS, if you're on a Samsung Galaxy tablet running Android, if you're on a Chromebook, if you're on a Mac OS based system, if you're on a Windows system, a Linux system, you can still read that email because it's using most likely one of two standards, either ASCII like we see here or Unicode. So that when we send this message across, if it's in ASCII, then we know what this information means. So if something actually starts with a pattern in the first 3 bits here, and let me go back and make sure my highlighter is actually turned on. There we go. So those first 3 bits. So if that equals a 0, 1, 0, then that means it's an uppercase character. If it equals 0, 1, 1, that means that it's a lowercase character. So we know from that beginning pattern what types of characters we're looking at. So if we take this and then we convert those remaining values that exist there. So if I look at these values, if I have a 1, 1, 1 in the last 3 bits there, then that is going to be equal to the number 7 in decimal. 1, 0, 1, that is a 5. And then 1, 0, 1, 1. So if I look at these, and we'll be seeing a lot of examples of things like this throughout the sessions as we're looking at IP addresses and subnet masks and how network devices communicate. So we'll be looking at binary in the future as well. But I look at this in columns, so I have values that equal 8. There's nothing for my value that would be a 4. There's a 1 on the 2 and a 1 on the 1 value. So I take 8 plus 2 plus 1 and add those together, and then I have a value of 11. So now we have 7, 5, 5, 11. So if I take that 7, 5, 5, 11 and I kind of count up through the alphabet, if I go A, B, C, D, E, F, G, so a 7, that is equal to the G. So we do the same things for the other ones, and we see that spells the word geek. You have to be one in order to read this. So we have standards like this to allow communication no matter what device you're using, no matter what vendor you're interoperating with. You have the ability to communicate back and forth. And networks are based around these same types of standards. If we did not have these standards in place, then you would have to have your whole network based around one vendor. So if you were going to deploy Ruckus in your network, not only would you need Ruckus switches and Ruckus routers through the entire network itself, but you would also have to have Ruckus interface cards in all the PCs that we're trying to communicate. So it's very important to have industry standards to base communication around. And this kind of shows us some of the base standards bodies that are used in the networking industry. So again, a little bit of alphabet soup, just kind of like we had last week with LANs and WANs and CANs and MANs. Here we have a lot of different groups or entities like the EIA, or Electronics Industry Association, the IEEE, the Industry of Electronic and Electrical Engineers, the IETF, the Internet Engineering Task Force, IAB, the Internet Activities Board. So for example, what we just looked at, ASCII is a standard that is developed by the American National Standards Institute, or ANSI. So we've just seen an example standard that comes from ANSI. Now, from a networking perspective, there are mainly 2 bodies that we really focus on for networking standards, and that is the IEEE and the IETF. So now this is not a hard and fast rule, but as kind of a general rule of thumb. The IEEE handles standards that occur at layer 2 and lower, and we'll be talking a lot more about layers as we make our way throughout today's overall session. So layer 1 and layer 2, that's your physical layer. So that is the types of cable that's being used. That is the actual voltages that go on the wire itself. Layer 2 is switched communication. So last week we talked about switches and hubs and routers. So switches occur at layer 2. So most of that communication is controlled by the IEEE. So you may have seen standards like 802.1d, 802.1s. Those are standards from the IEEE. Not only do they control standards around Ethernet, but also standards around things like Wi-Fi. So anything in the 802.11 working group. So the IEEE is broken into separate working groups that each have their own area of focus. So, and this also includes things that we don't generally connect with standard networking, things like 802.15, which has evolved into what we call Bluetooth today. So there's a lot of different standards groups or bodies that are formed within the IEEE itself, and they are recognized by those category numbers. The IETF handles most of the standards that are layer 3, so that's where routers reside that we talked about last week. So they handle routing and higher. So things like HTTP that we just gave as an example, that is a standard that is controlled by the IETF. So let's look at some of these just real quickly. So let me bring up a browser really quick. So let me shift our view back to kind of the overall global view here for a second. And then let me bring up a browser. Okay. So here we see the home page for the IEEE. So, and you'll see there's a lot of different sections, a lot of different areas that you can look at on the IEEE's site. So you would mainly be looking at, standards that they develop. Now with the IEEE is a membership body. So there are tons of different standards controlled by the IEEE, but you'll see if you go in and you look to find standards, and take just a moment as that is popping up. So if I look through standards for something like 802.1d, which we'll be talking about in later sessions, which is spanning tree protocol, we will actually see different versions of the 802.1d protocol. And you can go in and you can get more information about these standards. Now, one thing to kind of note around standards through the IEEE. So many of these standards, or I would say most of these standards, are not available free of charge. So if we go through and choose by this standard, we'll actually see to get a copy of 802.1d 2004, that is $288 unless you have an IEEE membership, in which case it's $233. So the prices on different standards will differ quite a bit. So another standard that I pulled up here, let's see, I think I still have it up. Yes, I do. So like the 802.3 2018, this is the standard that includes 2.5 gig Ethernet, 5 gig Ethernet, what we call the multi-gig standards. So buying a copy of that standard is a little bit over $1,100 US. So unfortunately, if you compare this to the Internet Engineering Task Force, the standards are not as freely available through the IEEE, and they've changed their stance on this several times throughout their history. For quite a while, anything that was already an approved standard was available to review for free, but they have kind of shifted back to more of a purchase model. So for a while, anything that was a draft or anything was proposed, you had to buy into. Anything that was a standard, you could freely look through the standard itself. You can no longer kind of freely look through the existing standards. You do have to purchase those from the IEEE. However, there is a lot of freely available information, and a lot of that you'll find through IEEE Spectrum. So if you go through Spectrum Online, this has a lot of different educational information about numerous different standards that are controlled by the IEEE itself. One example here that is a great one is 5G, robotics, autonomous vehicles, and the eternal problem of latency. And this is actually through the IEEE Radio Spectrum podcast. So it's got a great discussion on how latency impacts networks and communications, and how that's going to affect a lot of different industries going forward, whether that is remote surgery or other things that are very, very latency sensitive. The time between the sending device and when that signal is received is very important from a networking perspective. So of course, I would recommend the Ruckus podcast if you're looking for a podcast to listen to, but another great one is Radio Spectrum from the IEEE organization. Now, on more of kind of an open side, you have the IETF, or the Internet Engineering Task Force. So, and this is kind of all of the standards that make up the internet itself. So again, most of the things that we deal with in a networking context that are layer 3 in the OSI model and higher, and we're going to look much closer at the OSI model here shortly, most of those are controlled by the IETF, or the Internet Engineering Task Force. Now, you can get some information from IETF.org. However, they're going to point you across to a different website to actually look at the standards themselves. So if you want to actually look at a standard, so you can go to Internet Standards and go to RFCs, or Request for Comments. Now, when you're searching for specific RFCs, or you want specific information, this is actually going to carry you across to rfc-editor.org. And I've pulled that up right here. This is an incredibly useful site for anyone involved in the networking industry. So this is where you would go to find out more detail about any of the routing and higher level standards that are used in networking environments. So if we come out here, I can search RFCs up here in the upper right hand corner. So if I want to learn more information about domain name resolution in DNS, I can do a search on DNS. And as you look through the RFCs that come up, when you're looking to find out more about a protocol or how a protocol functions, you want to look over here, see this is your standard number, and then look under the more information category. So I see right away that this is obsolete. This is no longer the standard for the domain name system, or DNS. So this was obsoleted by RFC 2821. So I don't want to look at anything prior to 2821. So I will scroll down in the list, or I can actually just do a search for the RFC number. And if I do 2821, so here I see that this was obsoleted by RFC 5321. So now I could do 5321. So this one is the current standard. I can see there are updates to it, but it's not been obsoleted. So if I want to learn more about how DNS functions and communicates, I can go and I can read the entire content of that standard. And this is not just true for that. This is true for anything like OSPF. If I want more detail on how OSPF works, then I see it was originally RFC 1131 that was obsoleted by 1247. So if I come down here, 1247, that is OSPF version 2, which is the main version in use for IPv4 traffic, for standard IP addresses and standard IP routing. So I can take a look at RFC 1247, bring up the text of that. So you can see as you go through, it tells you kind of at the beginning, what is the protocol about? What is the protocol's function? What is it going to do? What are commonly used terms and definitions used throughout this RFC itself? And then it actually goes into, kind of the overall listing of what is included in this RFC. Now this particular RFC is I think this one's about 212 pages in length. So if you're looking for detail about how OSPF functions, it all exists here within this overall RFC. So it talks about, so for here, it is looking at, lower level protocol support, primitives, tasking support. So if we keep kind of scrolling down throughout the information here on OSPF version 2, I'm looking for examples of, I believe this has some network diagrams. It tells you what all the different link state advertisement types are, what all of the different OSPF packet types are, what all of the different area types are, what are all the different values included in OSPF messages, and how are those values interpreted, how do two routers kind of initiate the communication between each other. This shows the different states right here that they go through and what occurs in each of these states as they're beginning to communicate. And most RFCs with something like this will also have, keep scrolling down and show examples here of packet formats, usually kind of towards the bottom. There we go. So not only can you find out like how these devices communicate, but you can also see exactly what is included in every single OSPF packet. So this shows you the exact number of bits that are used for all the information included in that, and it shows you descriptions of what all of these mean. So you'll know exactly what is sent in every different type of OSPF packet, how many bits or bytes are used to contain that information sent between peers. So regardless of the level of detail or depth that you're looking for on a particular protocol like OSPF or like HTTP, you'll be able to find that in the RFCs themselves, because these are what make the actual standards. So not only is this just what's available to you as the public, but this is the exact same thing that vendors use to be able to implement these protocols on their devices individually. So, and I'm going to give everyone a little bit of homework for this week. So an RFC to read. Let me do this one. So there are a lot of RFCs that are also informational as well. So if someone wants to go out and read an RFC just to get familiar with, how RFCs are broken up and what type of information is included, a great one to read is RFC 2795, which is on the Infinite Monkey Protocol Suite, or IMPS. So this RFC, it's a humorous RFC that was actually created and kind of pokes fun at the overall tech industry for things like running out of IPv4 addresses, and how you could create a limitless numbering system and use that for communications. So there are some great ones out there that are just humorous in nature, such as this one, but it's a relatively shorter RFC. It's just about like 14-15 pages. It is very humorous in nature. It's a really funny read. And it also kind of gets you familiar with how RFCs are laid out and how it shows you like packet structures and how it kind of builds diagrams in ASCII text to be able to understand how to read and interpret the information that are in Internet Request for Comments. So, and again, if you're looking for something a little bit more relevant or specific, you could look for things like HTTP to understand how HTTP functions. And, again, these are standards around things like a 404 means that you couldn't find the page that you were looking for. So what are all the different error codes that are included in a service like HTTP? If you want more detail on that, you can find it directly in the RFCs that actually define the protocol and that protocol behavior. And these are all freely available to the public, that anyone can read the RFCs and anyone can publish an RFC as well. So the whole idea of the internet on its creation was that, entities could work back and forth freely to be able to create and develop standards for how communication will take place and occur. So then I'll shift back into the PowerPoint view here real quick. Let me make sure that has shifted appropriately there. Sure has. And then let's talk a little bit about the OSI model itself. So sure, we've got all these standards, but where do they fit? Where do they fall in communications, and how do standards interact with each other? And that brings in the concepts of the OSI 7-layer model, or the OSI model. So in the OSI model, this breaks up network communications into 7 logical layers. Now, some of the layers underneath this may have sublayers, and we'll talk a little bit about that as we go through and look at examples of different types of communications that occur at the different layers within the OSI model. And we've talked about a number of these layers already. So last week when we were talking about routers and switches and cabling, we talked about the physical layer, or layer 1, that was the cables themselves. So there are a lot of standards there that are things like, what is the difference between a Cat5 cable and a Cat5e cable and a Cat6 cable? So that deals with the voltage patterns, it deals with the types of media that's used to transmit that data over. For Cat5, Cat5e, Cat6, it'd be like the number of twists that are occurring per meter of the cabling itself. What is the maximum distance of cabling which can be used? All of that deals with the physical layer. When we move up from that, we get into the data link layer. So we have Ethernet. This is where switching is taking place. Layer 3, that is where IP takes place. That is where routing is going to happen. So understanding kind of the order of this is very important to understanding how networks function and how communication is logically broken down. So if we go from the bottom up, we've got physical, data link, network, transport, session, presentation, and application as our 7 layers. So there are some kind of ways to kind of help memorize the order of these. So if we're going from the bottom up, PDNTSPA, one kind of useful learning exercise for that is people don't need to see Paul Allen, which will make a lot of my my Mac friends happy on the session to hear that as the overall example. Or if you go from the top down, another very common mnemonic that is used for memorizing these layers is all people seem to need data processing. So kind of use that to help memorize and understand these layers and the order in which they exist. So now that we've seen what the layers are, let's talk about each layer in a little bit more depth and what is occurring at those individual layers. So we'll go from the top down, because that's exactly how communication is going to occur. So we start out with the application layer, which is creating an application message. This is going to be based around standards that have been created. Some of the common standards that operate here include HTTP, FTP, DNS, Telnet, SSH. These are all layer 7 applications. Now, a lot of people, when they hear the application layer, when they hear layer 7, they kind of misconstrue that to believe that that their browser may be layer 7, or a web server itself is layer 7. So let's say that's an Apache server or a Tomcat server or IIS. That actually sits above. So an individual application or an individual like server service, that would actually be up here a little bit above where this model ends. But it's going to be designed to talk to layer 7 directly. So when you open up your web browser and you type in www.comscope.com, that is creating an HTTP request. So your web browser is talking to the application layer. A common thing that's said in networking is that you have a layer 2 issue. So there's a problem with switching communication, or you have a layer 3 issue. There's a problem routing traffic from one destination to another within your environment, and you may hear at times people say that they have a layer 8 error or a layer 8 issue. They're usually using that to refer to the user. However, that could also refer to the application that's in use. So not the application protocol, but the individual application. So we could think of the user, the person sitting in the chair, that we're really layer 9. We sit as the next level above the application. We're typing data into the application. I opened up and I typed in www.comscope.com in my browser, but I only put in one M. Well, that's a layer 9 issue. I typed it wrong. The browser malfunctioning, that would actually be kind of like layer 8. Now, those aren't defined. Those aren't real values. And usually when someone says layer 8, they mean it is a user mistake. So again, at the application level, we've got a message. So just like I mentioned earlier, this controls things like what are the different error messages? What are the different what HTTP calls methods. So if I open my browser and I again type in www.comscope.com and I hit enter, that is going to send initially a head request for the root object on that server. So it's going to ask for a / or the root object to try to look at the information for that home page. So that head request sends the headers of that information. So I would then compare those headers to any browser cache that I had locally to find out, do I have some of the elements from that page? Do I have the most recent copy of that information? If so, I can simply display that from my browser cache. If not, then I can do a GET message. So a GET message says, send me the full page, send me the full information. All of those methods and how they're encoded, that is all part of the HTTP standard, which is a layer 7 standard. Which then brings us into the presentation layer, or layer 6. So this includes a lot of different things like MPEG, JPEG, GIF, TIFF, ASCII, Unicode. So remember I said we were sending a message to a web server. We were asking for the homepage for comscope.com. Well, I need to understand how that request is encoded. So if I look at, again, if I look at those values in binary, if I don't know that that's ASCII, then I don't know how to interpret that information. I don't know how to convert that into text. So you'll take the request that you're sending over to that web server and you're going to encode that, in this case, as ASCII. You know, you also want to be able to see a picture that's on that website regardless of what platform you're on. So whether your phone happens to be Android or whether it happens to be an iOS-based device, you want to be able to view that information. So that's why we have things that are common encoding types like JPEG, GIF, MPEG, that all exist here at layer 6. So we don't want to build that into the layer 7 standard. And this is why the OSI model is important, is because we can have these and they can be completely independent from what's running at layer 7. You don't want to have to build into HTTP, how do I encode an image? You know, how do I encode a request? There's no reason to rebuild all that functionality because it's already out there. ASCII already exists. We already have a method to take simple text and convert that down into binary in a way that it can be translated back on the other end, and the other end can see that that is GET /. So give me the root object from that web server. Same is true if I want to look at a video on YouTube. If you're watching this live stream, it is being encoded in H.264 or another encoding method that exists at layer 6. So you're using layer 7 right now. You're using HTTPS. So that's going to be your initial request to go out and join into this live stream. But underneath that, it has to say, okay, the request itself is ASCII. That's how you're formatting the request that you're sending. The information that's coming back out to your browser is being encoded in H.264 or another encoding mechanism for this video and audio transmission. Now, if you're going through YouTube, that is also a secure website. So this is where we get into the idea of sublayers as well, because we have to encode the request in ASCII or the information that's being sent across as a streaming video or audio transmission. We need to encode that first before we can encrypt it. So SSL exists at layer 6, but we have to do that other encoding first. Then we get to the SSL portion. Then we get into the actual encryption of the information that's being transmitted so it remains private as it is sent across the internet. So then that moves us from the presentation layer down into the session layer. There's not as many common protocols as you may be familiar with that run directly at the session layer. Some protocols that are here are point-to-point tunneling protocol, L2 tunneling protocol, PAP, remote procedure calls, SOCKS. So a lot of these are forms of VPNs that can give you virtual connectivity to a remote network, and a lot are specific requests that can be sent to a server to take an action, like remote procedure calls or RPCs. One thing you will see a lot more commonly, though, is the transport layer. The most common protocols you deal with here are TCP and UDP. So TCP is used for a good bulk of communication and conversation, but UDP is used a lot for things like video. You know, TCP ensures that you always have guaranteed delivery of the packets themselves. So if you're going out and you're downloading an application from the Microsoft Store or from the Apple Store or from the Google Play Store, if you're downloading that application, you have to make sure you get the entire thing. Any single packet that got lost in transmission, you need to send a negative acknowledgement to say, hey, I missed packet number 47. So that would cause packet number 47 to be retransmitted. So those behaviors exist here at the transport layer. So UDP is unacknowledged. So that is not connection oriented. Well, why would we want something like that? UDP sounds bad. Don't we want to always get the full transmission? Well, if you're watching a streaming video and it dropped a couple packets, which would cause just a little bit of pixelation on 1 or 2 frames, is there any reason to send a message to say, hey, I didn't get packet number 47, please send that over to me again? Not if it's real time. So it depends on where you're watching or what you're watching. So if you're watching something like a video on Netflix and you already have a set of cache that's been built up, then yes, you probably do want all the packets. But if it's a real-time stream like we're doing right now, then that frame is already gone. It's already passed. So if that's a VoIP phone call, so you're calling someone on the phone and you're communicating with them in real time, it doesn't make any sense to retransmit a packet, because by the time you tell the sender to retransmit and it's sent it back across the network and it's received, you've already played that part of the audio transmission. There's no way to go back and fix that. So UDP is used for a lot of types of real-time communications. So again, here we do see some kind of ideas of the breakout of sublayers as well, because you could be using TCP or UDP along with IPsec or transport layer security, which are other forms of encryption. So traditional HTTPS that used SSL encryption, that occurred at layer 6. But there was a lot of movement within the overall industry to say, you know what, we want to be able to encode this at a lower layer, so that way we can take this same security and we can apply that to a lot of different types of protocols. So TLS occurs here at layer 4. So then we move into layer 3, which is the network layer. So as we make our way down, we see over on the right-hand side there, these have changed from messages into segments when we looked at the transport layer, and you're kind of breaking these down into smaller pieces and you're encapsulating as you go down throughout this process. And we'll talk a lot more about encapsulation next week. So, but here we actually get a packet, which is something we're far more familiar with, that we send IP packets across our network. So this is where routing is going to be taking place. So different protocols that work here at layer 3 of the network are IPv4, IPv6, network translation. So you're probably going through a network translation layer right now watching this live stream. So if you're doing this from home, like most of us are in the current global health situation, so you actually have packets going from you to your local router that are using private range addresses. So your local IP address is probably something like 192.168.1.12. Well, a lot of other people have that same address at home. They're using that same range of addresses. So to make sure it gets back to you specifically, you use network address translation on the router that is connected to your service provider out of your house. That is another layer 3 function or feature that translates your internal private range addresses into a public range address so that you can access things like the CommScope website and like YouTube. So there are a number of other protocols that would have existed here previously, things like IPX on older Novell networks. So IP is not the only way that has ever existed to communicate from a routing perspective, but it has become the predominant standard. So early on, when you had things like Banyan Vines, Novell, they had their own methods of routing traffic. They had their own logical addressing systems. But as the internet became more and more prevalent and IP became more widely distributed, most of even those vendors transitioned over to using IP in place of their own underlying protocols. Which then brings us down to the data link layer, or layer 2. So this is where you have things like Ethernet, ATM, token ring, frame relay, link layer discovery protocol, spanning tree protocol. And again, you kind of have sub-layers that exist within this. So spanning tree protocol or link layer discovery protocol, those would run on top of something like Ethernet. And Ethernet can kind of bleed through a little bit here. You've got the logical idea of Ethernet, which incorporates things like MAC addresses. How do Ethernet devices communicate with each other? What is the format of an Ethernet frame? That you start out with a destination MAC address followed by a source MAC address. All of that is part of the layer 2 component of the Ethernet standard. The Ethernet standards also bleed down into layer 1 because those standards do include things like, what is gigabit Ethernet and what are, the individual wires that are used? What are the pinouts? What voltages are being used to transmit data? So it kind of can bleed between kind of your layer 2 communication and your layer 1 communication. Even something you might traditionally think of as purely layer 1, something like PoE, power over Ethernet, that includes signaling that is logical that occurs at layer 2. So the ability to understand what device type is out there and what are its power requirements, that kind of bleeds up from the physical into the data link layer. But then down at the physical layer, instead of any longer looking at frames, now we're just looking at the individual bits and bytes, and we're really looking at voltage patterns or RF patterns. So examples of things that are down here, again, like specific Ethernet standards for like 1000 base TX, things like Cat5 or Cat6 cabling, Wi-Fi 6, all of these would exist at the physical layer, although they may have some logical components that exist at the data link layer or at layer 2 within the OSI model. Which then brings us into the idea of how do we put this all together and how do we make sense out of this? And again, what is the value that exists within this? Like, why are we learning the OSI model? Why does every time every network vendor goes out and teaches you a network class, why do they teach you the OSI model? So let's look at some just generic communication as an example and see how this flows through the model, and then see what would happen if the model didn't exist. So I've got a client that is going to try to connect to www.commscope.com. So I've opened up my web browser, I've put in that address, and that is then going to send from the web browser, it is sending down to layer 7, to HTTP. So it's sending an HTTP GET request. So it's saying GET /, just like we talked about earlier. Well, again, just like I said earlier, I have to know how to encode that. I have to encode it in a way that the server on the other side of this connection will be able to understand it. So we're going to choose our encoding method as ASCII. So that would actually match my earlier example because it starts with GE. So the first thing would be 0100000111 would be like the first letter of that if we were encoding it in ASCII. So let's say this is HTTPS. So at the presentation layer, it would also be encrypting that communication as well, so it remains private. So in this case, we're not doing anything at the session layer for this communication. So this is going to talk then directly down to TCP. Now, since we were hitting HTTPS, it depends on where that security is taking place. Are they implementing it as TLS or are they implementing it as traditional SSL encryption? If it's TLS, then it would actually be here at the transport layer would be where we're actually encrypting this. So, but now I'm going to encode this into a TCP segment. So I'm basically taking it, I'm putting everything, I'm encapsulating it, so it's kind of like a remailer service that I'm mailing off a letter and they're putting it in another envelope and then mailing it further. So, or you can think of it like a Russian nesting doll. You've got a smaller doll inside a bigger doll, inside a bigger doll, inside a bigger doll. So I then move that into the IP layer. Now at this stage, we're actually going to start doing a lot of logical decisions. So when we get to the IP layer, that local client is going to be looking at this and deciding things based off of the IP address. So it's going to look at that IP address and find out, is this message meant for me? One of the concepts of the OSI model is this should behave the same whether you're dealing with local communication or remote communication. So maybe I'm actually running the web server service locally on my system and I'm trying to talk to that local web server service. So if the address was my own, then as soon as I get down here to the network layer, I would recognize that as my address and I would send it back up the stack to talk to that server service that's running locally on my system. In this case, the web service for www.comscope.com is not running on my local laptop right here. So I found out, okay, that's not me. But where is it? So I look at my IP address along with a value called the subnet mask that we'll talk about later on in these sessions to determine, is it on my local network? Is that server somewhere here inside my house? It finds out that nope, it doesn't match the range of addresses that are used in my house. So I need to send this to my gateway. I need to send it to the router that's attached to my network. So as I send that down from IP down towards Ethernet, it now gets encapsulated into an Ethernet frame. So I took the IP packet, I put that into an Ethernet frame, and the destination address is going to be my local router that's attached to my service provider. So now that I've taken and I've encapsulated all those requests all the way down there to that data link layer, now I can send that frame out. Now keep in mind, this may not be a direct connection. I already said this is not on my local network. So in the case of my network, I have a switch, then I have a router. Now along the path, there's probably going to be multiple switches and routers that exist. So, but I'm going to be sending to the MAC address that's here on the port on my local router that points towards my laptop. So that's what I put onto the physical wire. That's the Ethernet frame is destined towards my router. That Ethernet frame is not destined towards www.comscope.com. So as it goes through that switch has MAC tables, so it's learned those hardware addresses of the devices on this local network. So when that frame is received here, it knows which port to send it out. So this is the same as the bridge communication or bridge conversation that we had last week in our session. So I know to put it out this port to get to my local router. So when I did that, I took that bit and byte data that was down there at the physical layer, and I went back up to layer 2. So this came back up from layer 1 to layer 2 when it went through the switch. When it gets to the router, that router's got to make a very similar decision to what I did originally. It's got to look and find out if the destination IP address is itself. So it finds out, nope, I'm not the web server for www.comscope.com. So I need to figure out how to forward this. So it's going to go up. First of all, at layer 2, it's going to recognize that it is the destination. The MAC address, the hardware address of the destination, matches itself. So it knows it has to look at it rather than forwarding it from a layer 2 perspective. So then it de-encapsulates that information and comes up to layer 3. Then it looks at that destination IP address, and we're assuming here that we've already done the DNS resolution. I've already looked up the host www in the comscope.com domain, so I know its destination IP address on my laptop that originated this communication. So, but it's going to find out in its routing table, where does that destination reside? So then it comes back down, so each time you go up, you come back down. So here we went all the way up to layer 3, we came back down, we re-encoded the data again at layer 2, and then have taken that back to layer 1. So it's being written again as, you know, either a wireless signal that's radio frequency based, or as a wired signal, which could be fiber optic, or could be electrical signaling on copper media. So as this makes its way towards that destination, there are many times that it's going to go back up to layer 2, down to 1, 2 to 1, 3, 2 to 1, 2 to 1, 2 to 1, 2 to 1, 3 to 1. So it's going to keep going up and down these layers for each switch or router that it traverses through along this path. So once it has gotten to the local network where that server resides, now as it goes up the overall OSI model, it's going to see the frame, I am the destination. It's my hardware address is the destination. When it opens that, the IP packet, for all intents and purposes, there's going to be one difference that it's going to see here. But it's going to be the same contents that existed on the left. The one difference will be a value called the time to live, or TTL, that each router within that path reduced that time to live by 1. So that way, if there were loops in an environment and you couldn't find the destination, that packet wouldn't simply keep going in a loop forever. So the TTL has been reduced, but other than that, the IP packet is the exact same thing that my laptop originally created. Now, as I go farther up the stack, so I look at IP and I see I am the destination IP address. So I then send that up the stack further to go to TCP. TCP, I'm looking to make sure that I got all the packets in sequence that make up this overall request. If it's just a simple HTTP GET request, then it'll be just one packet. So there at the segment layer, that's also telling me what service does this need to communicate with, because it's going to have a destination port number. So in this case, we're HTTPS, so it's going to be port 443. So that's how it can differentiate between a number of services running on the same server. Is this a DNS request? Is this someone asking for an IP address via DHCP? Is this a request for the sorry, just a second. Sorry, didn't quite reach my mute in time there. Apologize. Is this a DNS request? Is this for the web service that's running? You know, what is this request? So it's able to look at that destination port to determine, oh, okay, this is an HTTP request. So that will come up. Again, the TCP was the exact same thing that was encoded over on the left. So as I open these, I'm getting the exact same information that was originally written. So as I come up, then I've got to, since this was SSL, we'll just say here it was traditional SSL. So as I get up to layer 6, I'm then going to decrypt that traffic. Once I've decrypted it, I identify that it is written in ASCII as the format. So then I take that binary string and I convert that over into the actual request, which again, it was the exact same thing here, the exact same thing as far as the ASCII was concerned, and that request that I wrote originally, that get forward slash, what the server receives is the exact same thing that I originally wrote. The server response is going to work in the exact same way. So it will actually take the HTML of that page. It is going to encode that as ASCII or as Unicode. My initial GET request will actually identify what encoding methods I can understand, so it knows which formats can be used as part of that information being sent back towards the client. So it will actually take, let's say, the home.html, say that's our root page. It will take that home HTML content and it will encode that down as ASCII. It will send it with a HTTP status OK header. So that shows us kind of like the similar to 404, 504. It's going to show status OK. It's going to actually write everything in as ASCII. It will encrypt it. It will put that into TCP segments, which will use the SYN and ACK values that had already been defined. So we know this is the next packet in sequence. It will then encode that in IP to go back towards my client, which writes it in Ethernet that points towards its upstream router. And the same thing happens on the way back, that this goes many times to layer 2, to layer 3, to layer 2, to layer 3, to go all the way back to the client. So now I receive in my browser the CommScope homepage. So, and again, the reasons why this is important is if we did not have kind of this logical breakout, even if we were based around industry standards, but we didn't have this OSI model, then if I wanted to make changes in how something like HTTP functioned, I would have to build the whole stack. I would have to choose, like, this is how I encode data. This is how I, convert text into binary. I would have to redo all of that function, and I would have to make sure that every client that wants to view a web page has the newest HTTP. And that, feasibly would include that they have to get a new network card, whether that's USB based or however I'm connecting to my system. They have to get a new network card in order to use that new version of HTTP, which would be massively inefficient. And we see a lot of examples of this in the real world. So a couple of clear examples is Ethernet is not the only medium that I could be transmitting traffic over. So we saw earlier ATM, frame relay. There were a lot of other things that existed there potentially at layer 2. Well, as long as you design it to talk to the layer 3 standard, we don't care what you're using there. And in this communication example, it may not have been Ethernet the whole way as layer 1 was concerned. I might not have a physical connection on my laptop. I might be using Wi-Fi. So at the data link and physical layers, I was using Wi-Fi 6 to send that up to my local router. It then wrote that in DocSys. So that was, again, a different protocol that's being handled as far as the physical layer is concerned. The carrier may go through a couple hops of DocSys before they convert that into Ethernet. Another carrier within the path may be using ATM or frame relay. Not as common anymore as it was years ago, but it still could be happening. So as long as you design to just talk to that layer above, you don't have to worry about the rest of the layers. So you could create a new layer 1, layer 2 set of protocols and standards, and you could actually just make that talk to IP. As long as you make it talk to IP, you know it will be able to communicate to web servers. You'll be able to send email over it. You'll be able to send many different forms of communication, not just one form of communication that you wrote the standard for. Another clear example of where this model has been completely integral to the evolution of networks is around IP itself. Remember, one of the big problems we've had with IP for many years now is running out of addresses. So we went from IPv4, and IPv6 has been introduced as a standard because we just didn't have enough IPv4 addresses. If the OSI model did not exist, then we would have to rewrite everything with networking, including HTTP, including DNS, including all of the other layers. But it's not TCP v6, it's not HTTP v6. The only thing that had to be rewritten was IP, was just layer 3. So they adapted it to be able to talk up towards TCP, so they could carry a TCP segment so that TCP knew how to encode data to write it down to the IP layer with that new IP version 6, and they didn't have to touch any of the other layers of the OSI model. There are hundreds, if not thousands, of additional standards and application types that they didn't have to touch at all in order to implement IPv6 as a new standard. If it wasn't for the OSI model, then it would have been pretty much impossible. We would have had to have completely ripped out networking globally and started over again. So that is why the OSI model is important, and also just in day-to-day communication, in day-to-day discussions about networking, you will constantly hear people refer to, from a troubleshooting perspective, troubleshoot layer 1 first, look at your physical connections. Then go to layer 2, look at your switch network, then go to layer 3. You'll hear things like layer 4 through 7 load balancers, which is an example that we talked about last week. So you'll hear these layers used when talking about how networks function. Keep in mind, however, that TCP/IP has its own model. So we've been focusing on the OSI model because it's the most widely used logical model. But officially for TCP/IP, it's 4 layers. It has the link layer, the internet layer, the transport layer, and the application layer. So kind of the first 3 layers at the top of the OSI model, those all map into the application layer from a TCP perspective. Now it's good to kind of understand that the models do not directly map to each other, but even though you're using TCP/IP, I would strongly recommend that you keep your focus on the OSI model. Because when people say something like layer 3, they're talking about routing. They're talking about IP. They're not talking about transport layer. So they're talking about layer 3 in the OSI model. So even though, yes, the official TCP/IP model would be 1, 2, 3, 4 as your 4 layers, and boy, that was really horribly written. Let me do that again. 2, 3, 4. There we go. That's not how anyone refers to these in practice. So yeah, it's good to understand that TCP has a different model, but really focus your understanding over here on the OSI model, because that's how people will refer to network communications. So with that, let me shift back over here to our schedule. So today we talked about different standards bodies and which ones are relevant to networking discussions and communications. We focused a lot on the IEEE, as well as on the Internet Engineering Task Force, or IETF. Next week, we're going to be talking about key infrastructure protocols. So what are other protocols that are necessary for your network to be functional? So we're not going to talk about really the protocols from the perspective of it's running on your switch or running on your router, but it has to be running somewhere inside your infrastructure on another server to have a healthy network. So these include things like DNS to be able to resolve a name like www.comscope.com back to an IP address to allow you to communicate with it. Things like SNMP, Telnet, SSH, HTTP, which we already used in our examples today, FTP, DHCP, network time protocol, and ICMP from a diagnostics perspective. Again, we will not have a session the week of Thanksgiving in the United States on November 27th. We'll pick back up on December 4th, where we'll go into a lot more detail on, what do frames actually look like? So what are what are all the fields within Ethernet frames or within IP packets? How do we encapsulate and decapsulate that data? On December 11th, we'll be looking at physical layer standards, PoE, PoE+, PoE++, PoH, and neighbor discovery. On December 18th, we'll look at Ethernet specifications and communications. Of course, the most important one that we'll be doing will be the week after that, on December 25th. You don't want to miss that session. No, we'll actually be taking off December 25th and January 1st, and then we'll pick back up in the new year. So that gives us kind of a picture of what we've got coming up. I hope you found the session useful and informative, and definitely any feedback that you have on these sessions, please let us know. You can email us at ruckuslive@comscope.com. And thanks everyone for attending, and I will see you next week when we take a look at key infrastructure protocols. Thanks everybody.